Oh, this feels good today. This feels like we are at the end of a very long journey, and we've learned so much. And I wanted to start by thanking you for coming along with me on this journey. So today I want to talk about organometallic reactions in organic synthesis. And you know, we get to the end of the course. We've gone through this wonderful carbonyl chemistry, which is sort of the core of synthetic organic chemistry. It's logical. We've learned these beautiful ways of looking at molecules and recognizing various functionality, recognizing beta-hydroxy carbonyls and alpha-beta unsaturated carbonyls, and seeing this beauty of putting molecules together. And we've seen how these types of synthetic reactions, like the Robinson annulation, can be used to build up the types of structures that are in steroids and all sorts of medicines. We've gotten a little bit of a taste of some of the chemistry of amines and some of the chemistry that can give rise to alkaloids and bioactive nitrogen-containing compounds. And now I want to come back to synthesis. So we spent a little time talking about sort of natural biomolecules, sugars, which brought us in a beautiful refrain on stereochemistry and molecular conformation, polypeptides, which showed us just a hint, just a taste of not only the structures of biologically important peptides and proteins, but also just a taste of how chemists can build up molecules even as big as HIV-1 protease containing 99 amino acids. And one of my laments in teaching sophomore organic chemistry when I started teaching a sophomore class 20 years ago was there's all this beautiful contemporary chemistry that's going on that really is excluded from the curriculum. And your textbook does a wonderful job of bringing back one facet of this contemporary chemistry. That is the use of organometallic reagents and reactions in synthesis. Realize that the field of organic chemistry is a dynamic field. This is not something that's static. This is not a frozen body of knowledge. This is something that researchers like Johnny and Kim continue to develop new ideas, new reactions, new molecules, and to solve unsolved problems. And synthesis is about problems because there is a real need to build molecules. And we've gotten a hint of sort of old-style organometallic chemistry. We've seen Grignard reagents and organolithium reagents. We've seen how powerful these are as nucleophiles. And now we're going to see different ways of putting molecules together that in some cases are less, I'll say, logical in the sense they don't necessarily exploit natural reactivity in the same way, but they can stitch together what might be non-obvious bonds. So let me start by just mentioning a Grignard reagent here and a Grignard reaction just to take us back. And so if you have an alkyl halide, we learned that if you treat it with magnesium metal, usually an ethereal solvent, diethyl ether or tetrahydrofuran, the magnesium reacts. It sticks itself into this carbon-alkyl bond. In the process, it's actually going from magnesium metal oxidation state 0 to an alkyl magnesium halide where the magnesium has an oxidation state of 2. And we're going to come back to that refrain. But right now, I want to focus on a traditional organometallic reaction. So if you take some carbonyl compound, a ketone or an aldehyde, I'll write it sort of generically as this. It could be acetone, it could be an aldehyde, could be any other ketone. And then we carry out an aqueous workup, usually with acid. You could use water too if you really wanted to. I think your textbook typically writes it. But something to add a proton to the oxyanion that forms. You formed a new carbon-carbon bond. And if I had to characterize this chemistry, I'd say that the Grignard reagent, or other organometallic reagent like an organolithium reagent. So I'll put it sort of more general as organometallic reagent acts as a nucleophile for carbon-carbon bond formation. And this is very powerful because building up organic molecules really is a large part of what synthesis is about. Forming key carbon-carbon bonds, controlling stereochemistry, controlling regiochemistry, manipulating functional groups as you need them, taking, for example, a secondary alcohol to a ketone as you need it, or taking a ketone to an alcohol, or reducing a ketone or an alcohol down to a hydrocarbon. These are all sort of standard transformations, and a lot of the main processes that drive the building that sort of are layered on top of this are the carbon-carbon bond forming reactions. Well, I want to introduce now a different concept, and I'll introduce it in such a general way that I think it really is more a statement of philosophy at this point than a particular reaction. But imagine for a moment we had something a little bit different. Instead of transferring your nucleophile, your R group, your R minus, if you will, to the electrophile directly, in other words, just having the metal as something that makes it so you effectively have a carbanion. Imagine for a moment now you have two R groups on a metal, and this is characteristic of the chemistry of transition metals. And really, palladium is sort of the archetype of this, although we'll see it with copper. And then imagine that we spit out a carbon-carbon bond. And so I'll go like this, and I'll put parenthesis plus getting your metal back in some form. So this is a little bit different if you think about it, in the sense that it's not transferring. The metal is doing something different than acting as a nucleophile or transferring an alkyl group. You could say that the organometallic complex, so this is an organometallic complex because you have metals bonded to, or alkyl groups, organic groups bonded to a metal. You could say that the organotransition complex acts sort of like as a template. To bring the two R groups together. I'll say it can act as a template for CC bond formation. And in a way, this is no reaction in particular. We'll come to particulars, and I'll really focus a little bit more on mechanism when we see the Suzuki reaction. But this is kind of a concept or a theme. And one thing you'll notice is the idea of a metal acting as a template. the idea of a metal acting as a template really ends up being about the metal taking itself out of the two R groups and leaving a bond. And if you notice, in a way, this is the opposite of this step over here, where the magnesium is sticking itself into a bond. And as we approach this chemistry, we're going to see two reactions that are the opposite of each other. Oxidative addition, which is a metal sticking itself into a bond, much like we see with the magnesium here, as I said, increasing oxidation state from 0 to 2. And then the metal taking itself out of a bond, which we call reductive elimination. I'll get on to that more in a little bit. So when I put this lecture together, I wasn't sure how much I'd have a chance to cover. And initially, I figured we might get to cover section 26.3, but I've cut that out. Honestly, I want you to get the flavor of some modern chemistry, not all of the details. Your chapter starts with some really old organometallic chemistry, organocuprate chemistry, so I'm going to talk about that. We'll talk about organocuprate reactions, and then I want to talk about two Nobel Prize-winning reactions, the Suzuki reaction, which we do in my advanced laboratory class. It's a beautiful reaction and a powerful reaction. And the Grubbs, what's technically olefin metathesis, although its name is often associated with Bob Grubbs. Your textbook in section 26.3 also talks about the Heck reaction, which is a little more conceptually complicated. I decided to drop it out. I didn't want to flood us. I wanted to give us a taste, not an entire meal here. All right, so let's let's start talking about organocopper reagents. Now, we got a tiny little taste of organocopper reagents back in chapter 20, and I think that's one reason it's nice to see them again. So we learned, and this is, I'll just write what I wrote in chapter 20. We learned that we could form organocopper reagents from reacting an organolithium compound with a cuprous salt. Copper iodide is the salt. Cuprous iodide, copper 1 iodide, is the salt you learned about in your textbook, and that's fine. So 2 equivalents of an alkylithium plus cuprous iodide, CuI, gives you R2CuLi, plus, if you want to balance your equation, lithium iodide. As I've mentioned many a time, organic chemists are bad about writing this. I'll write plus to show it's both of them. We call this an organocuprate reagent. And if I wanted to write the structure of this, you could think of it as 2 R groups on copper with a negative charge on it. Kind of the same theme as I talked about there, and you'll see how that theme comes in the chemistry that I'm about to introduce. Lithium is the counter ion. We call this an 8, a cuprate, because when you have a negative charge on a species, you call it an 8. So this is a cuprate because you have a copper minus charge on it. And so some of the chemistry we learned about cuprates was we learned they could modulate the reactivity in 1,4 versus 1,2 additions. So we learned, for example, that if you had cyclohexenone, if you treat it with, say, methyl lithium, the methyl lithium adds to the carbonyl group to give an alcohol at this position. If we treat our cyclohexenone, however, with lithium dimethyl cuprate, CH3 2CuLi, so the organocuprate reagent you would get from adding methyl lithium to cuprous iodide, and then you carry out an aqueous workup. I'll just write H3O plus. Usually a person would throw dilute acid in. What's really special about the cuprate is that instead of getting 1,2 addition, instead of adding directly to the carbonyl group, we get conjugate addition. We get a Michael addition reaction. And after workup, your product of the reaction is the 3-methyl cyclohexanone. And so already that brought in the concept that copper had special reactivity, and it brought in this concept of control. And we see the concept of control with copper in other places as well, for example. So again, in chapter 20, I introduced another reaction, a special reaction of acid chlorides. See, normally if you take an acid chloride or you take an ester with a metal organometallic reagent like an organolithium reagent or a Grignard reagent, you can't control the reactivity. If I take an acid chloride like benzoyl chloride and I try to add one equivalent of methyl lithium to it to get acetophenone or one equivalent of methyl magnesium bromide, it doesn't work because the resulting ketone is still very, very reactive. And so you get reaction to add a second equivalent of methyl lithium to give 2-phenyl-2-propanol, and you get other reactions. Same thing with an ester here. Very hard to control the reaction to add just one equivalent of nucleophile. But we learned a special reaction of cuprate. So if I take lithium dimethyl cuprate, I'll write again 1CH3 2CuLi, and then we carry out an aqueous workup. What's beautiful about the cuprate chemistry is that we go ahead and we get a controlled single addition to give acetophenone. And so that gave us a new manifold of control. People have known about copper chemistry for a long time. Organocopper reactions have been investigated since well before World War II, where copper was discovered to modulate the reactions of Grignard reagents in some of the fashions that we've seen here. What I want to do now is to exploit or discuss another carbon-carbon bond-forming reaction that was developed later, I think the 60s, that gives us something that's less recognizable in terms of conventional nucleophile-electrophile chemistry. In conventional nucleophile-electrophile chemistry, you can at least in your mind's eye say, well, I can see the carbonyl is an electrophile, the organocuprate is a nucleophile, I can see putting them together. In the conjugate addition, in the Michael addition reaction, you can also, the 1,4 addition reaction, you can also say, okay, we learned that an enone was electrophilic at the beta position as well as the carbonyl position. I can understand putting them together. But now I want to show you another reaction. I'm going to draw it in a super analogous fashion so you see what's weird about this. All right. So imagine for a moment that instead of taking benzoyl chloride, I take 1-chlorostyrene and I subject it to the same reaction conditions. Lithium dimethyl cuprate followed by some sort of aqueous workup with acid. Now, you'd look at this if this were a Grignard reagent, and you'd say, well, you know, vinyl chlorides aren't electrophiles. We know that while we sometimes can have SN2 displacement by organometallic reagents in a conventional SN2 reaction, for an example, a sodium acetylide salt reacting with methyl iodide to get alkylated, we know that sp2 hybridized carbons don't participate in SN2 type reactions. And yet, something very much akin to what I've written on your left-hand blackboard occurs on your right-hand blackboard here, where your cuprate reagent does indeed react to form a carbon-carbon bond. And that's special, and that's weird. I'll write my aqueous workup in parenthesis. Your textbook doesn't include it. Honestly, most people would do it to hydrolyze the copper salts, but unlike, say, a reaction where you're generating an enolate, as in the first case up on top where it's absolutely essential, here an aqueous workup isn't essential. So, you know, you could say, all right, I don't care if I write it too much. All right, so what's happening here? Well, I've been hinting at this notion that metals can act as a template. So in sort of a general sense, we're having some sort of halide. This can be an alkyl halide, it can be an aryl halide, it can be a vinyl halide, and we're having some type of cuprate reagent. So I'll write this like so. And what we're doing is we're forming a carbon-carbon bond. So as I said, this is interesting because we're talking about alkyl, primary or secondary, or sometimes secondary. I'll say primary methyl, or sometimes secondary for our halide, but also vinyl and aryl, in other words, a benzene ring. In other words, we're doing a reaction not only at things where you might expect the conventional SN2 displacement, but also a lot of compounds like this vinyl chloride compound where you wouldn't expect a conventional SN2 displacement reaction. So I'm going to say not SN2. All right. So what's special in this chemistry? What's special in this chemistry is that the copper is mediating the reaction. The copper is facilitating the reaction. And I'm not going to go into a detailed mechanism. I'll give you a mechanism for the Suzuki reaction, but I want to show you the gist of it. So the gist of it is that copper acts as a template. That in addition to having the two methyl groups around the copper, like so, during the reaction, the copper also attaches itself to the vinyl group, basically just like magnesium sticks itself into the copper, into the alkyl carbon bond in forming a Grignard reagent. The intermediate here, which I'll draw as such, maybe I'll put it in a bracket just to remind us that this is not a stable compound, that this is only an intermediate. This intermediate forms, and what it does now is the copper serves as a template for formation of a bond between the methyl and vinyl group. The copper brings those two together, very much like that sort of generalized reaction I wrote in the very beginning. Now, as I said, this chemistry can occur not just with typical sort of SN1-like alkyl halides, but also with things that would, or SN2-like alkyl halides, but also with things that would never, never, never participate in an SN2 reaction. And so one of the features with vinyl halides is that the reaction is stereospecific. In other words, stereochemistry is retained about the bond of alkenyl halides. The example I gave you has no stereochemistry to the double bond, but of course double bonds come in flavors cis and trans when you have two different groups on the ends of them, or two groups on the end, one on one end and one on the other. So if we imagine for a moment that we, instead of having the halogen at the 1 position, have the halogen at the 2 position, and I'll just for the heck of it, make it a bromide. And again, imagine that we subject this to a cuprate reagent. Just to show you some of the diversity of cuprate reagents, let me give you a vinyl cuprate reagent. So I'll give you divinyl cuprate, so 2 vinyl groups bound to a copper, and then a workup, H3O plus. Now, what's interesting about this is we started with the trans stereochemistry about this bond. We're going to transfer this vinyl group over to this bond, and we retain the stereochemistry. In other words, the product we started with trans, and we've ended up with trans. And that's kind of cool, and that's kind of significant. So we're still trans. And conversely, if I started with the cis alkene, and subjected it to the same reaction conditions, so I'll just put a ditto mark here for the sake of saving space. Now we would get the other stereochemistry. In other words, the stereochemistry of the alkenyl halide has dictated the stereochemistry of the product. Here we're trans, or E. Here we're cis, or Z. All right, I kind of want to, at this point, summarize the cuprate chemistry, and I'll just go ahead, and since we see a lot of chemicals here, a lot of different compounds, I want to just show you maybe what a researcher would do in the laboratory. So let's say for a moment that the goal was to synthesize this compound. These types of vinyl compounds with stereochemistry about double bonds are present in insect pheromones. You can make chemical compounds that will lure and trap bugs by synthesizing their pheromones. These are used to kill Japanese beetles and other sorts of pests. And so let's just take a look at what a person would do in the laboratory. So they'd want to make a cuprate reagent, so they'd take a halide, like a vinyl halide, and they'd treat it with lithium metal. Remember, 2 equivalents of lithium metal is required to react with a halide to give an organolithium reagent. So I would get vinyl lithium plus lithium bromide if I wanted to balance my equation. In the second step, I would add cuprous iodide. And if I wanted to balance my equation, which, as I said, organic chemists often don't do, we would take 2 equivalents of lithium iodide, and we'd treat it with cuprous iodide to get the cuprate reagent. And the final step, you would typically do this all in one flask. You would make the lithium reagent. You would add the copper iodide to make the organocuprate reagent. And now, in the final step, we would take our styrenyl bromide and treat it with our cuprate reagent. Maybe do an aqueous workup on that. I'll just put that in parenthesis here. To get our product. Thoughts or questions? One thing that's bad about cuprate chemistry is of the 2 vinyl groups on the copper, the 2 R groups on the copper, you only transfer 1 of them. So it's wasteful as far as the chemistry goes. You waste half of your vinyl bromide in this chemistry. Another thing that's bad about the copper chemistry is copper's a toxic metal, and it's expensive. If you're making medicinal compounds, you don't want any metals to be left, and you certainly don't want metals sticking in that are toxic. So one of the things that chemists have been trying to do is to make chemistry more efficient, make it go by use of 1 equivalent of reagent rather than having to use 2 equivalents of reagent, to avoid the use of toxic metals, and to avoid having to use a whole equivalent of a metal that's expensive or that's poisonous, and to just have that metal template act as a catalyst. As I said, cuprate chemistry was really developed in the 1960s, and it's sort of old organometallic chemistry. And so I want to fast forward us ahead now through what's really a modern organic chemical reaction, the Suzuki reaction, a modern organometallic reaction that largely achieves the same transformation. And the big innovation of the Suzuki reaction, well, one of the big innovations of the Suzuki reaction was instead of using an organolithium compound as a metal, was to use an organoboron compound as a metal. We've already seen that organoboron compounds are very easy to access. You can access them by hydroboration. You use them all the time in hydroboration oxidation chemistry. Boron is environmentally benign. It's not toxic. Or boric acid, for example, can be bought in the drugstore to use as an eye wash. It's not a harmful or poisonous chemical, unless you're a cockroach, in which case it's very good for killing them. All right, so the gist of the Suzuki reaction, the other big innovation was to use a catalyst rather than a whole equivalent of metal. So we're going to take something that looks very similar. We're going to take a halide. Often we're talking a vinyl or an aryl halide. In some cases, it can be an alkyl halide. And one of the active areas of research is making the Suzuki reaction more compatible with more different types of compounds. And we're going to combine it with an organoboron compound. And typically, the boron has a couple of oxygens on it. I'll call these OR prime groups. We're not going to get into all the details. I'll show you one later on. This is an organoboron compound that's called a boronic ester or boronic acid, depending on whether there are alkyl groups or OH groups. And the last piece of the puzzle is a palladium catalyst. Now, when people write organometallic reagents, or organometallic, I should say, reactions, often they want to focus on the big picture. And we're going to see that as we work our way through the mechanism. And often there are variations that don't matter a whole lot. So I'm going to write this for now as L sub n m, or perhaps, I guess, since we're only focusing on the Suzuki reaction, which is always done with palladium, I'll write L sub n PD. And I'll just refer to this for now. I'll give you an example of one in a moment, but I'll refer to this right now as a palladium catalyst. And so the big idea of the Suzuki reaction is that we're going to use the palladium catalyst as a template to combine the R group on the boron with the R group on the halide. And the overall result is we're going to form a new carbon-carbon bond very efficiently. In my synthetic organic laboratory class that students take in their junior or senior year, we do a Suzuki reaction. It's a cool reaction. They really enjoy it. And the reaction they do is to take a bromostyrene that's been prepared for them by the teaching assistant in a stereospecific fashion through an elimination reaction. It's prepared by bromination of cinnamic acid, followed by elimination. And they combine it with an organoboron reagent that they prepare themselves, also in a stereospecific fashion by hydroboration, with a boron that has a boronic ester that has a benzene group over here. This is called a catechol borane. And the palladium catalyst that they use, well, I'm going to give you a variant of the catalyst. We use a palladium-2 catalyst, but I'm going to give you a palladium-0 catalyst. Basically, I wanted to simplify some of the doesn't matter a whole heck of a lot which palladium catalyst to use. And I wanted to simplify things a little bit and sort of align them with your textbook. And so the palladium catalyst that we'll use in this particular example is tetrakis triphenylphosphine palladium. Those triphenylphosphines are ligands on the palladium. They represent the ligands shown over here. Again, we're going to skip over some of the details. When the catalyst is resting, there are 4 triphenylphosphine ligands around it. When it's doing its thing of bringing the metals together, there are 2 triphenylphosphines around it. But that isn't so important. We also need a base in this chemistry, and this is typical of the Suzuki reaction. I've sort of written things in a general form here in an unbalanced equation. And the product of this Suzuki reaction is now just forming a new carbon-carbon bond. So we have the half that came from the alkenyl halide and the half that came from our organoboron reagent with our double bond and our C4H9 group, our butyl group over there. So this is 1Z3E 1-phenyl 1,3-octadiene, if you want to know the name. I'll write a balanced equation, and we'll talk a little bit about how the components form. The other components, the byproducts, if you will, the waste products of the reaction, are the boronic ester now with an ethyl group. So technically, it's a boric acid derivative or a boric acid triester derivative. And the other product of reaction is sodium bromide. And just to remind us that we're using only a little bit, only a couple of mole percent of palladium, only about 1 mole of palladium for 50 moles of molecule. I'll write that this is a catalyst here, so I will just remind us of that by writing CAT. Kind of an abbreviation there. What's cool about this chemistry is it brings us to new types of reaction mechanisms. So it's cool because it's useful. We can readily snap together 2 halves to make a big molecule, and in a way that you really haven't seen before. That's powerful. But another thing that's cool about the chemistry is that it brings in some reaction mechanisms that you haven't seen before and yet have some familiar themes. So I want to break the mechanism down into 3 main steps. There's also 1 minor step that I'll insert when I show you the mechanism in detail. So I'll say 3 main steps in the mechanism. The first step is called oxidative addition. In oxidative addition, the metal sticks itself into the alkenyl halide bond, into the carbon halide bond. The second main step is transmetallation. In the transmetallation step, the other alkenyl group is transferred from boron to the metal. Transmetallation, it kind of makes sense. It almost says that. And the third one, the third step, is where the metal acts as a template, and that's called reductive elimination. The metal spits out the carbon-carbon bond. And as I hinted, even though you haven't seen organopalladium chemistry, there's a lot of analogy to chemistry that you've seen. And that's really what I want to focus on, because I think that embodies some of the beauty of this very powerful chemistry. So as I was hinting, the palladium can go ahead and lose a couple of those triphenylphosphine ligands. And so the active carrying catalyst is not the tetrakis triphenylphosphine palladium 0, but the bis triphenylphosphine palladium 0. It's just a ligand dissociation reaction, but don't worry about it. But this then is the I'll say the active form of catalyst. And technically, that's going to be the species as we write the mechanism that we're going to focus on. All right, so this active form of the catalyst can react with the alkenyl halide. So there's our bromostyrene. And as I said, the reaction's called oxidative addition. In an oxidative addition reaction, a metal sticks itself into a bond and increases its oxidation state by 2. We have the carbon-bromine bond. We have the palladium. The palladium happens to have a 0 oxidation state at this point. When the palladium sticks itself into the carbon-bromine bond, it increases its oxidation state to palladium in the +2 oxidation state. I gotta write that a little bit neater. I'm not doing a good job at being neat here. All right, so we have 2 triphenylphosphines, PH3P2, palladium. Now the palladium has the alkenyl group bond bound to it and the halide group bond bound to it. And even though this reaction involves palladium, even though you haven't seen organopalladium reactions before, this reaction is just like the formation of a Grignard reagent. In a Grignard reagent, magnesium starts at oxidation state 0. You add into the alkyl halide bond. Now you have the alkyl group and the halide group bound to the magnesium, and the magnesium's at the 2 oxidation state. Even the notion of ligands isn't very different. When we talked about Grignard reagents, we said you have to form them in an ether solvent because the magnesium needs those ether oxygens as ligands on it. Well, palladium likes ligands that have more diffuse lone pairs and can participate in other types of interactions, pi back bonding interactions. And so as a result, you have phosphorus as a ligand rather than oxygen. All right, that's the oxidative addition step. So here I'm going to again write our organopalladium intermediate. And now a step occurs that's not super important as far as this mechanism goes, but it's facilitating the transfer to the boron. We have sodium ethoxide as a base. In other words, in terms of the big concepts, it's not as much of an issue of this templating process. It's more of a mechanistic detail. A ligand exchange reaction occurs. That means ethoxide does basically what you could think of as an SN2 displacement and kicks out bromide. I'll write this on the next line because these structures are pretty big. So we're going to just replace the bromine with an ethoxy group. And if I wanted to balance the equation, I suppose I'd say that sodium bromide is also a byproduct of this reaction. Okay, now the next main reaction, the transmetallation reaction. And so at this point, we're going to transfer that R group from boron onto the palladium. In a way, it's like another one of these SN2 displacement sort of like reactions I talked about. Okay, so here's our palladium species in the cycle. And here's our organoboron compound, our boronic ester. And our structures are so big that I'm going to now move to the other blackboard. So I'll draw an arrow, and we'll continue our arrow over on the next board. Maybe I will give a name here. As I said, our step is transmetallation, so I'm going to write transmetallation. We're going to transfer the ligand from the boron, which acts like a metal, to the palladium. So we still have our styrenyl group on the palladium. And now what we've done is transfer our alkenyl group from the boron to the palladium. And again, if I'm going to balance my equation, the byproduct of this reaction, the ethoxy group, comes off the palladium and onto the boron. Boron really likes to be bound to oxygen. Because boron has a vacant p orbital, any atom that has lone pairs on it is a friend of boron because those lone pairs donate into the boron. And so this ends up, the ethoxy group that we transferred before in the ligand exchange reaction ends up facilitating the transmetallation reaction. The final step is the reductive elimination step, the step in which the metal is acting as a template. And so we have our species here, PH3, P, PD, styrenyl, with our alkene group. And now, in the reductive elimination, it's the mechanistic reverse of the oxidative addition, as I've been hinting at again and again in our talk with the copper and other things. Now we're going to take the palladium out and form a bond between these two carbon groups. And the overall result then is going to be our, I should write it a little lower so that you can see it well. Now we're going to have our alkene, our diene, our 1Z, our 1E3, our 1Z3E, 1-phenyl octadiene, and we get back our palladium catalyst, and it's dropped to the zero oxidation state. And this is really, of course, the hallmark of a catalyst. The catalyst goes through the reaction again and again and again. So the catalyst is available now to react with another molecule of alkenyl halide, to have another ligand exchange occur, to have another transmetallation occur, and finally to undergo reductive elimination again and again and again, dozens and even hundreds of times in the catalytic cycle. Let's take a look at how we might use the Suzuki reaction in organic synthesis, and I'll just pose a sort of a sample question here. Let's say I was thinking about how we synthesize this molecule. And I'll say, let's synthesize this molecule where we have a methoxy on a benzene linked in a meta fashion to a transalkenyl group connected to a C5H11, a pentenyl group. So let's say synthesize this compound from compounds containing 7 carbon atoms or fewer. And if you look at this, of course, I've deliberately kept this kind of analogous because you're just beginning to learn this chemistry. But you might look and say, oh, okay, this doesn't look that different. In other words, we kind of could see how this piece could come from an organoboron compound, and this piece could come from a halide. And it would all be chemistry that we know. So if I draw my retrosynthetic arrow downward and think about things going backwards, I could say, imagine that we formed this bond over here. And imagine we did so breaking the molecule into 2 convenient halves, each of which had half the molecule. So I could have 3-bromomethoxybenzene as 1/2, and I could have a boronic ester as the other half. Like so. And I could bring these 2 halves together, so I guess I'll put a plus sign and say, oh, I could see how I could do that by a Suzuki reaction. And then you might say, well, look, he said 7 carbon atoms or fewer, and I know we've got too many here because I've got 6 carbon atoms on this boron piece and 7 carbon atoms here. But we've learned the hydroboration reaction. We've learned that it's stereospecific. And so you'd say, I could imagine forming this bond here by a hydroboration, and we could think backwards some more and say, okay, if I hydroborated 1 heptine and reacted it with catechol-borane, I already have hinted that that's a readily available organoboron compound. It also conveniently contains fewer than 7 carbon atoms. Now I could imagine hydroborating heptine in a stereospecific fashion to give us the trans compound, combining it with my bromoaromatic in a Suzuki reaction. And I could put this all together in a forward sense. So in a forward sense, sort of solving our synthetic problem, I'll start with heptine, hydroborate it with catechol-borane. You just mix them together, heat them typically if you really want to make the reaction go quicker. That gives us our C5H11 alkenoborane. Like so. And then I could imagine combining that boron compound and our bromomethoxybenzene, which we won't talk about how to make, but fortunately I've given you a chemical supply house that provides chemicals up to 7 carbons. You know how to make it from your amine chapter, but you don't need to because I've given us a nice chemical supply house. And we'll take our tetrakis triphenylphosphine palladium catalyst, and sodium, I'll write that it's a catalyst over here just to remind us we're only using a little bit, and a full equivalent of sodium ethoxide. And the overall result now is that we've synthesized our target molecule. And because of the power of this chemistry, in 2010, Suzuki won the Nobel Prize for this, along with Negishi and also with Heck, who invented the Heck reaction that we're not going to talk about. So this is really powerful and useful chemistry for forming carbon-carbon bonds. So one of the journals I like to read is the Journal of Organic Chemistry. Journal of Organic Chemistry is where people publish contemporary organic chemistry research. And there are usually pictorial abstracts in the journal so you can see what's going on in the article. You can learn more about what's going on before you read the entire paper. And it seems that I can't pick up a copy of the JOC, of the Journal of Organic Chemistry these days, without seeing at least a couple of examples of the reaction that I'll show you next, the reaction of olefin metathesis that won Bob Grubbs and Dick Schrock the Nobel Prize in 2005. So the olefin metathesis for a long time had been an object of curiosity, just a weird reaction. And then organic chemists, notably Grubbs and Schrock, started to try to exploit and to understand the chemistry. And here's what we have today. The gist of the chemistry, I'll write it sort of in a semi-general terms, but not a fully general terms because there are so many variations. the gist of the chemistry is that we have two alkenes, the same or different depending on some subtle issues, and a ruthenium catalyst. And I'm going to write out the structure. We'll show you a little bit of a flavor of the mechanism of it. So I'll write this again in sort of the general way we did when we started to talk about the Suzuki reaction. Ln, meaning ligands, on the metal ruthenium, where the metal ruthenium is bound to an alkene group. And again, I'm going to write this as R. And when you have a carbon that's double bonded to a metal, you call it a metal carbene. And so this is called a ruthenium carbene catalyst. The catalyst that these days is used is called Grubbs catalyst. After Bob Grubbs, and because this is such an active area of research in his laboratory, there's a first-generation Grubbs catalyst, a second-generation Grubbs catalyst, a third-generation Grubbs catalyst, as well as Grubbs-Hoveda catalysts and other variations of it. But the main thing, the main feature of the Grubbs catalyst, of the ruthenium carbene catalyst, is you have a metal double bonded to carbon. And what this metal does is it participates in a very amazing partner swapping dance. And in this partner swapping dance, the metal swaps partners with the alkenyl groups, and ultimately the alkenyl groups swap partners with each other. And again, writing this sort of in a generic fashion, again, there are sort of various variations on it. We get a new alkene, generally as a mixture of cis and trans isomers. In which the two original alkenes have now joined to each other. They can be the same or different or in a molecule, and it sometimes depends. And the other piece of this partner swapping, in the way that I've written it, is that you get a molecule of ethylene. And typically, since ethylene is a gas, it goes away, and you've basically now kept the main parts of the molecule together. Let me give you a specific example, because it's a little hard to absorb in the vast generality. If I take the molecule 1-hexene, like so, and I treat it, and I'll show you the Grubbs first-generation catalyst. Honestly, for your purposes, that's all you need here. The ligands on the metal, we've already seen ligands of halogen on a metal. We've seen ligands of phosphorus on the metal. Here we're now seeing a ligand of a carbene on a metal. The Grubbs catalyst has a couple of chlorines on the metal. It has a phosphine, and typically the phosphine is tricyclohexyl phosphine, and there are two of them bound to the ruthenium. And then I'm going to draw out, the first generation Grubbs catalyst has a benzene group over here. And we only use a little bit of the catalyst. So that's going to swap partners, but it'll go away. It'll basically get swapped out of the catalyst in the catalytic cycle. So I'll remind us this is a catalyst. And the overall product of the reaction then is we're going to join our two hexenes together and blow out a molecule of ethylene, which is going to give us a molecule of 5-decene. So if you can count to 10, I'm just drawing a 10-carbon chain here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'll say it's a mixture of cis and trans isomers. typically, when the Grubbs reaction goes intramolecularly, and I'll show you an example of that at the end, you just get the cis isomer because of the constraints of the ring. And typically, if you have just two alkyl chains, you get a mixture of cis and trans, although controlling the stereochemistry is a key issue. So we have our 5-decene plus ethylene. And I think what really marked Grubbs' genius here, and Schrock, and even before that, I think his name is Chalvin, as well as Tom Katz, who was sort of the fourth man on the Nobel Prize, who almost won it. I think what marked all of their genius in looking at this reaction is the idea of saying, wait a second, I haven't seen anything like this sort of partner swapping before. And recognizing something's unusual, whether it's in chemistry or if you're going on to become a doctor or a medical researcher, whether it's in medicine or whether it's in pharmacology, and saying, wait a second, this doesn't fit the mold of what I've learned. Recognizing that is the grounds for big discovery. If you're in the area of understanding, sort of basic science, then you say, oh, I want to learn about it because I've never seen anything like this. If you're in an applied area, and synthesis is a little bit basic science and a little bit application, if you're in an applied area, you say, oh, wait a second, maybe I could use this discovery to do something. Maybe I could figure out something useful as an application from this. So I want to show you the gist of the partner swapping mechanism, and then maybe we'll look at a couple of applications in synthesis. So the gist of the partner swapping mechanism is that you have your ruthenium carbene, which I'm just going to write as I did in the very beginning, LNRU double bonded to an alkenyl group. And your ruthenium carbene reacts with another alkene to give a metallocyclobutane. I can draw arrows like this, like a cycloaddition reaction. I think that's fine for how we're going to think about it. A lot of times when you think about organometallic chemistry, one's focusing more on process than on mechanism. In other words, in SN2 reactions, you're thinking very much about the mechanism, or E1 or E2. In organometallic reactions, you're thinking a little more about a process. In other words, we're not worrying exactly how an oxidative addition occurs. We're just looking and saying it occurs. Okay, so now we do the exact same thing in reverse. In other words, this is a sort of a cycloaddition reaction. Now we do the reverse, and we end up going to LNRU double bonded to a CH2 group. And the other product that we've blown out of the reaction is our alkenyl group. And I'm not worrying about stereochemistry here, so that's our alkenyl group. If you don't like my writing the hydrogens in here, I tell you what, I can write it like this if you prefer, but basically I'm not fussing on whether it's cis or trans stereochemistry. Okay, now the partner swapping continues, and in the second step, so we've blown out half. And now we have a carbene where we have our ruthenium bound to a methylidine group, a CH2 group. And now in the partner swapping, we have another molecule of our alkene coming in. And again, we're going to make a cycloaddition reaction like so, to give a metallocyclobutane, like so. And now we do the reverse of the cycloaddition reaction, and we blow out a molecule of ethylene, and we get back our carbene. And this cycle continues over and over and over again as we drive the reaction, blowing out ethylene and driving the chemistry forward. So as I hinted before, this reaction often is used when two alkenes are in the same molecule to make a new ring. We've seen lots of rings. We've seen rings in steroids, other sorts of rings. And the ring closing metathesis, as it's called, or RCM, is a particularly powerful way of making rings. And so I'll diagram this sort of in a generic fashion first, where we have two alkene groups connected by some sort of tether. And we subject this to our catalyst. And again, I'll use our first generation Grubbs catalyst. Again, the details are something of which catalyst you'd use in which circumstances probably go a little beyond the scope of the course. And the overall result of the process now is we swap partners on the two ends of the ring. Like so. And form a new ring with an alkene in it. Your textbook gives a nice example, and then I think maybe I'll take 1 minute to show you an example of a thinking process. So your textbook shows the synthesis of a pyrrolidine ring in which it starts with diallylamine that has a tosyl group on nitrogen. It subjects it to the reaction conditions, and we form a 5-membered ring. And I think that's kind of a nice starting point for the sort of problem that I think you should be able to solve and to think about. So let me show you maybe a thought process. Let's say I want to synthesize this cycloheptene. With an alcohol there and a double bond. And let's say, just to put some constraints on it, I'll say from compounds containing 4 carbon atoms or fewer. And just to give us maybe a little hint, I'll say using olefin metathesis. All right. Now, you look at this molecule, and you look at the example on that blackboard, and you say, oh, okay, I can kind of see my way back. This is retrosynthetic analysis, and I've given you a big glaring hint. You say, I can see my way back to a compound in which I have, since we're forming a 7-membered ring, we're bringing together 1, 2, 3, and 1, 2, 3. I can see 1, 2, 3, 4, 1, 2, 3, 4. If I just imagine bringing these two partners together, you say, I can see that. And then you look, you say, well, we still got a lot of carbons in here. And you say, wait a second, okay, I'm thinking back to my organolithium chemistry. And I know that I can go ahead and add in to, say, an ester group, 2 equivalents of an organometallic compound like an organolithium compound. And I can choose any sort of ester like this, and now you put this together and you say, okay, I can go ahead, I can do this. I can go ahead and say, I will take, let's say, maybe I'll make my organolithium compound just for the hell of it. I suppose my parameters didn't require this. But I will take, let's say, my bromo compound. I'll take my bromoalkene with 2 lithiums. And this kind of ends up being a refrain for all the things we've done in the class. We make an organolithium reagent. We take our ethyl ester, that's going to be the top 2 parts, and we treat it with 2 equivalents of the organolithium reagent. So I'll just say organolithium reagent, parenthesis 2 equivalents, and then I do in a separate step an aqueous workup, and that's going to take us over to our building block. And now that's taken us all the way, and I just subject this to ring closing metathesis, which I write as RCM, and I have products. And it's that type of thinking that can lead you on. Last question.
Can we use magnesium bromide instead?
Could you use magnesium? Someone answer. Yeah, we could go ahead and make a Grignard reagent. And so here we've gone in the course all the way from Grignard and organolithium chemistry, through carbonyl chemistry, through amine chemistry, through the Grubbs reaction to build really complex molecules from simple building blocks. You guys are the greatest. Knock 'em dead on the final. I will see you on Tuesday. Wow me. I want to be wowed.